In this video, we'll look at these two formulae for electric force and electric field strength. To understand how to use these formulae, we'll apply it to a situation using parallel charged plates and charged particles within the electric field produced by these parallel plates. So let's start by defining each of these terms. We have the electric force. I'll give it a subscript E, is the force experienced on the charged particles within the electric field. And the units are in newtons. Q is the charge on the particle. This is in coulombs. Now, if the particle in concern is an electron, we can get the charge of an electron from the data sheet. So the charge on an electron is minus 1.602 10 to the minus 19. If we were talking about a proton, then it will be the same magnitude but opposite sign. So we'll assume this is an electron, and we'll say that this is a proton. Now, E gives us the electric field strength, which is in newtons per coulombs. But looking at this formula here, we can see that the electric field strength could also be volts per meter, because you've got the potential difference is, or voltage is in volts, and this is referring to the distance between the plates, and that's measured in meters. So that'll be volts per meters. So these are equivalent units. So 1 newtons per coulomb equals 1 volt per meter. And that's a good thing to remember. So I'll write those values here. We've got V is voltage, or we'll start to refer to it as potential difference in volts. And D is the distance between the plates in meters. Recall that these lines represent the electric field lines. They show the direction of the electric field. And the direction of the electric field is defined as the direction that the force that a positive test charge would experience within that electric field. So essentially, it goes from positive to negative direction, and it's the direction that a positive test charge would go under the influence of the force that it experiences within that electric field. So positive charges will be attracted towards the negative plate. So notice that a negative charge will experience a force in the opposite direction to the electric field. So when we look at this shortly mathematically, then the direction can also be indicated by a positive or a negative value. So a negative value would indicate a direction that is opposite to the electric field, and a positive value would indicate a direction in the same direction as the electric field. So let's now work through a sample problem. Let's place a proton here and say that we have a distance between the plates of 5 centimeters and a voltage across the plate of, say, 200 volts. So we want to be able to calculate the electric field strength and calculate the force acting on the proton. But after that, we'll also look at calculating the acceleration of the charge, the final velocity, and also the kinetic energy. So what we'll be doing is bringing in some of the formulae from kinematics. So starting with the electric field strength, what do we know? Well, we know the voltage and we know the distance between the plates. We need to put it in SI units. So this one's a simple substitution. So we write the formula as shown, then we substitute and solve. Okay, so now we'll go on and calculate the force on the charge. So what do we know? Well, we know from the previous part that the electric field strength is that, and recall that 1 volt per meter is equivalent to 1 newtons per coulomb. So we can write this like so. And we know the charge on a proton, which is the same magnitude as the charge on an electron, but with a positive charge. So using our formula written exactly as shown, we just again substitute and solve. And notice, because we've converted it to these units, we can cancel out the coulombs. We're left with newtons, which is the correct unit for force. So I'll stop the video there and come back to the next parts shortly.